Could it be that we're not the first to marvel at our sun? Imagine for a moment ancient alien explorers charting the cosmos, drawn not to Earth, but to the fiery giant at the center of our planetary system. Perhaps they saw it not just as a star, but as a colossal engine, a source of untamed power. They may have left, but the subject of their fascination remains, burning brightly at the heart of our solar system. When we look up at the seemingly endless expanse of the cosmos, dotted with countless stars, it's this one celestial body that singularly defines our sky and our very existence. It's no surprise that past generations of humans, inspired by its mesmerizing glow, wove countless legends to explain its brilliance. Today, with technology that has advanced far beyond their wildest dreams, we have the power to investigate the complex processes happening both inside and around our local yellow dwarf, probing its ferocious atmosphere in more detail than was ever previously possible. Let's begin a voyage into this intense environment to witness the incredible phenomena that take shape there. This exploration of the sun will use different wavelengths of electromagnetic energy, allowing us to see our star from a new vantage point. We've previously applied this method of using the electromagnetic spectrum to investigate Jupiter and some of its moons. Now we will use this technique once more, but this time our focus won't be a planet, but rather a tremendously energetic, gigantic sphere of plasma. The light we see is ancient. While light is the fastest thing we know of, the view we get of the sun from our earthly perspective is already about 8 minutes and 20 seconds old. This means we're always seeing the sun as it was a few minutes in the past. Even more astoundingly, if you consider the time it takes for a photon created in the sun's core to journey through every solar layer before finally escaping into space, the light that eventually reaches your eyes is anywhere from 10,000 to 170,000 years old. To start our investigation, let's begin with the sun's outermost atmospheric layer, the corona, much like you'd begin eating a piece of fruit from the outside in. This next image comes to us from the Solar Dynamics Observatory, SDO, a NASA space mission that launched in February 2010. The SDO's goal was to better understand the solar changes that affect life on Earth and our technological infrastructure by studying the dynamic solar surface and atmosphere in many different electromagnetic wavelengths. By looking at light far beyond the visible spectrum, NASA could see details that are normally invisible but are vital to our comprehension of the sun. This specific image was taken using a 19.3 nanometer wavelength, which is light in the extreme ultraviolet range, corresponding to a color temperature of 1 million Kelvin. We can clearly see the upper region of the sun's corona. Curiously, the sun's corona is also something that can be seen with the naked eye on very rare occasions, like during a total solar eclipse, when the moon is positioned perfectly between our planet and the sun. For a short time, the view of the bright central disk, known as the photosphere, is completely hidden, revealing a glowing exterior. While this is an already stunning sight, the corona is nowhere near as intricate as it appears in this picture from the SDO, which makes the SDO an indispensable tool for scientific discovery. Let's venture a little deeper to examine features of the sun located just below the corona. At a color temperature of 20 million Kelvin, the brilliantly bright spots represent events we call solar flares. Here is some video from a particularly active week for flares that occurred back in August 2022. Solar flares are immense explosions during which the sun discharges a vast amount of electromagnetic radiation. They happen when magnetic fields cross over, become distorted, and then rapidly rearrange themselves. This behavior is driven by the turbulent nature of the plasma inside the sun itself, where these magnetic fields originate. However, solar flares are not the only atmospheric feature of the sun that gives off radiation. Coronal holes marked by this darker area on the sun are another fascinating characteristic. We'll look at these more closely using extreme ultraviolet light. Coronal holes are regions of cooler, less dense plasma that are magnetically open. This means that instead of creating closed loops that circle back to the sun's surface, their field lines extend outward into the solar system. These areas allow solar wind particles to escape into space more easily. When these solar winds are aimed toward and strike Earth's magnetosphere, they create the magnificent aurora lights that dance across the night sky in our planet's polar regions. Using ultraviolet light gives us a vastly better view of these captivating features in the sun's outer layers. Light from the non-visible spectrum is an amazing tool, and there are many different features in the sun's outer layers worth observing. These include solar filaments, which are also known as solar prominences. They are massive loops of plasma that rise up from the sun's surface. These gigantic loops are large enough to make our Earth look like a tiny dot and can stretch for hundreds of thousands of kilometers into space. They might form in as little as one day, but a stable prominence can hang around in the corona for several months. In this footage, we can see a solar prominence twisting its way out of the photosphere and into the sun's atmosphere. Even though this video is sped up, making minutes seem like seconds, when you consider the huge size of the prominence, you realize just how quickly the sun's powerful magnetic fields are forcing this material to move. A fact you might not be aware of about the sun's atmosphere is that it sometimes rains. Not all of the charged plasma that gets thrown into the sun's corona continues its journey across the solar system. Some of it stays within the corona, getting trapped and cooling down until it falls back to the sun's surface as a shimmering rain. This coronal rain is a beautiful sight, but it's best viewed from far away as it remains millions of degrees in temperature. Gently returning to the sun's surface is the fate for only some of the sun's plasma. This is where the comparison to Earth breaks down. After all, on our planet, clouds don't snap like a stretched rubber band and shoot off into space. On the sun, thanks to tightly coiled magnetic fields, they do. This is a time-lapse of a coronal mass ejection, CME. Watch as the structure builds at the bottom left of the sun for a while before it finally snaps, sending billions of tons of plasma hurtling across the solar system. Even with our planet's magnetic field, being hit by a strong CME could be catastrophic for our satellites and electrical grids. All these structures are captured by the SDO, here using a 30 nanometer wavelength of light, which is in the extreme ultraviolet part of the electromagnetic spectrum. Timing is everything when trying to capture these features, as they appear more often in certain years than in others. In truth, every structure is tied to the sun's solar activity, which ebbs and flows in an approximately 11-year solar cycle. While a lot has been uncovered about the sun's outer layers, there's still more to find out. Just as using visible and ultraviolet light can show different things when looking at the same feature, using two different wavelengths of non-visible light can also be revealing. To illustrate this, let's look at these two pictures of the sun's corona taken over the same span of time. The next two images use different light wavelengths. The first, captured at a color temperature of 600,000 Kelvin, shows the quiet corona and highlights coronal loops. The second, taken at a color temperature of 2 million Kelvin, reveals the much hotter active regions of the corona. The stark difference between the two images highlights how important it is to use varied methods when studying the star. What might seem at first to be a single solar event can be revealed as a complex, interconnected series of events. We still haven't technically made it through the entirety of the Sun's atmosphere. Moving deeper, let's look at another image from the SDO, this time using a 160 nanometer wavelength of light focused on the transition region. The transition region is a layer located between the Sun's corona and the chromosphere, which is the lowest layer of the Sun's atmosphere. It's an incredibly thin layer, only about 100 kilometers thick. Inside this region, the thermal temperature of the Sun increases dramatically, from about 8,000 to 500,000 Kelvin. For a comparison here on Earth, incredibly hot lava flowing in Hawaii is 1,270 degrees Celsius or 1,143 Kelvin. The temperature at the lower, deeper end of the transition region is nearly 6 times hotter than that. At the upper end of the transition region, the temperature is over 346 times hotter. Traveling even deeper, we find ourselves in the Sun's chromosphere, the last atmospheric layer before we get to the Sun's surface. Pictured here using 170 nanometer ultraviolet light, it's estimated to be about 1,700 kilometers thick. Looking closely at the chromosphere, we can spot some mesmerizing features called spicules. Swaying like tall, wavy grass in the wind, these long jets of plasma shoot up from the Sun's surface at speeds up to 100 kilometers per second, roughly 282 times faster than the speed of sound, and can reach heights of nearly 10 kilometers, which is over 1 kilometer taller than Mount Everest. They form and disappear in about 5 to 10 minutes on average, and the processes behind them were mostly unknown and debated for a while, as it was unclear how magnetically charged particles could possibly break free from the Sun's magnetic fields at that depth. That was until 2017, when a team of scientists working on a highly detailed model of the spicules realized their origins must be connected to neutral particles. Scientists hadn't initially put neutral particles into their models of the Sun, as they didn't think they affected the movement of the magnetically charged particles. But once they were added, it turned out that the neutral particles gave the magnetically charged particles the unexpected buoyancy they needed to escape the Sun's plasma and shoot upward into spicules. Going down through the Sun's lower atmosphere, we finally arrive at the photosphere, the real surface of the Sun, which is best captured using visible light. While the edge of the photosphere looks sharp and clear, as it often does to our eyes, this is just because the Sun is so far away. The Sun itself is not solid at all, as it's far too hot for matter to exist as a solid, liquid, or gas anywhere in it. It can only be plasma, known as the fourth state of matter, and it's thought to make up 99.9% of all the matter in the universe. Plasmas usually act a lot like gases, except they're made of a mix of ionized atoms and free electrons. The photosphere is the outermost layer in this image, about 400 kilometers thick. It isn't a fixed solid edge of the Sun, despite what this picture might imply, and sadly, it's the deepest layer of the star that scientists can directly observe. Looking closer, you might see some dark spots on the left side. These are called sunspots, and they look darker than other parts of the photosphere because they are cooler, but that's only when compared to their scorching hot surroundings. Unlike coronal holes, sunspots show up in places where magnetic fields are especially strong. Here, heat gets trapped below the photosphere because convection is reduced in these areas. When we compare this picture of the Sun to an earlier one, taken with extreme ultraviolet light over the same time frame, a link between sunspots and solar flares appears. The captivating solar flares and sunspots happen in the same spot. By looking beneath the surface, it becomes clear that one must cause the other. Now let's get a closer view of some similar sunspots. This picture was taken by the Swedish Solar Telescope, located here on Earth, using a visible light wavelength of about 400 nanometers. Next to and all around the sunspots, the photosphere is filled with these jagged-edged, constantly changing cells which look a bit like lava as it cools and cracks. However, these cells are about 1,000 kilometers across and are known as solar granules. You can think of them as the top layer of a swirling convection cell below. The brighter spots inside each granule are fluid at unimaginable temperatures, rising from the sun's upper interior to its surface. When it gets to this boundary, the fluid has nowhere to go but out and across. After slowly cooling, the fluid sinks back down through the rough, dark edges surrounding each cell before starting the cycle all over again. This process is very similar to the convection currents in Earth's mantle, which are responsible for plate tectonics. This process is not a small one. While on average each granule is estimated to last for as little as 20 minutes, the flow inside the cells reaches supersonic speeds of more than 7 kilometers per second, creating waves on the sun's surface from sonic booms. Amazingly, these granules can also be seen in the full disk view we saw before, using the same wavelength of visible light. You might think this image looks quite grainy for such a high-tech space probe, and you'd be right, it does. But that graininess is the granules on the sun's photosphere, not a processing error or too much noise in the image. And that, unfortunately, is the end of our journey, as scientists have not yet figured out a way to see deeper into the sun with either visible or non-visible light. Much of what's beyond this layer is still wrapped in mystery. Even so, we can easily see the benefits of using light from all the different spectrums to study the sun. These methods let us see exploding solar flares, huge coronal holes, swaying spicules, fascinating sunspots, and shape-shifting cells, among other things, in completely new ways. The sun is humming with vibrant activity, and a large part of it would be invisible to us if it weren't for these imaging methods. Maybe one day we will find ways to look even deeper using techniques we can barely imagine right now. Just like those ancient generations of humans long ago could hardly picture the methods we are using today. But for now, just knowing there is so much unseen activity in the universe and having the tools to find it fills you with excitement and curiosity. Who knows what else might be out there waiting to be found? If someone were to suggest that the sun's cycles could deeply affect a whole life, the first thought might be a sudden turn from astronomy to astrology. While many people around the world believe that you can learn about your future by studying the positions of stars and planets, this channel mostly focuses on the natural beauty of space and the underlying mechanics that explain how it all works. However, sometimes you can find a piece of truth even in the most unexpected stories. Let's take on a predictive role for a moment, not as someone writing horoscopes, but to suggest that based on the sun's current state over the next few years, there might be a higher chance of experiencing poorer health, less dependable technology, warmer weather with fewer clouds, and possibly other surprising effects. How can this be claimed? Because it seems that the sun, that giant ball of fire in our sky, isn't just our energy source. Scientific research is starting to show that its 11-year cycles might actually act as a metronome, setting the rhythm of life on our planet. It's not surprising at all that the sun has a huge impact on life on Earth. In many ways, it's the very source of life. Life on our planet needs energy to exist, and the sun consistently gives us that energy. Light for plants, plants for herbivores, and herbivores for carnivores, all the way up the food chain. It's hard to think of anything on Earth that could survive without our sun. Yet, besides the priceless gift of this life-giving energy, it's easy to think of the sun as being pretty constant. We see it rise and set in the sky every day, but we rarely see it go through any noticeable change. This, however, is a deception. The sun is always changing. As our scientific knowledge grew and we learned how to shield ourselves from the sun's most intense glare, it became possible to study the sun's surface. As far back as 1610, it was clear that the sun was a turbulent, shifting sea of barely contained plasma, which often broke free despite the powerful gravitational force holding it all together. The nuclear reactions in its core are so incredibly hot, reaching 15 million degrees Celsius at its center, that plasma bubbles and bursts on its surface, erupting into solar flares that blaze in every direction. Sunspots, dark patches on the sun's surface filled with strong magnetic fields and ranging from 1,600 to 160,000 kilometers across, form, drift, and disappear. Coronal mass ejections, CMEs, explode out of the sun's corona, the atmospheric area above the sun that is bizarrely 200 times hotter than its surface. It's tough to find a place in the solar system as active as the sun. What many people don't know is that this activity rises and falls. The sun follows an 11-year cycle that goes from a period of low activity, called the solar minimum, to a much higher level, the solar maximum, and then back down again. Sunspots, solar flares, and CMEs all happen more often during the solar maximum. You are 50 times more likely to see a solar flare during solar maximum than during solar minimum. And large CMEs become more frequent, going from happening once every few days to several times in a single day. This is called the Schwab cycle. Interestingly, this is just one half of a bigger cycle known as the Hale cycle, which charts the changes in the sun's magnetic polarity. Once every Schwab cycle, every 11 years, the sun's magnetic north and south poles switch places. When another Schwab cycle happens, the poles switch back. This constant push and pull of solar energy levels pulses through our planetary system, rising and falling like a heartbeat. And surprisingly, even though we can't see it, we here on Earth move to its beat. The exact reason why the sun has this cycle is still largely a mystery. It's clearly tied to the magnetic processes happening inside the sun itself. Yet, even after watching these cycles for the last 200 years and seeing signs of their effect on Earth over the last 10,000 years, we are no closer to figuring out why the solar cycle has this specific length instead of any other. What force is behind it? With no other clear explanation, some scientists have tried to link the orbital period of Jupiter, which is also about 11 years, to this cycle length. However, this could just be a coincidence. Although Jupiter has 2.5 times the mass of all the other planets in the solar system combined, and certainly has some gravitational effect on the sun, its orbit can't completely explain the seemingly random changes that the sun's cycle goes through. A lot of what happens inside the sun is still a puzzle to us, but its effect on Earth is much easier to see. It starts with the space around us. Space is becoming more and more essential to modern civilization, so it shouldn't be a shock that CMEs and solar storms coming more regularly from the sun would affect the technology we've put up there. Scientists can predict when a solar storm, also known as a geomagnetic storm, will arrive days or even weeks ahead of time. This warning lets astronauts get to safe shelters to protect themselves from dangerous rises in radiation levels, and also allows the delicate hardware on satellites to be shut down to prevent damage. This is vital, as solar radiation can create unexpected electrical currents in wiring, overloading systems that haven't been put into a safe standby mode. But there's another part of geomagnetic storms that you might not expect. Some of that radiation affects the atmosphere itself. It warms it up, though only slightly. As the atmosphere warms, it expands, and this affects our satellites in space. In the vacuum of space, there's almost no drag, so things can orbit almost forever. While that's not completely true, satellites in low Earth orbit do need to use fuel to fix their orbits about 4 times a year, as there's still a tiny bit of atmosphere up there. But when a geomagnetic storm hits, the atmosphere expands upward, and low Earth orbit satellites have to adjust their position every 2 to 3 weeks to keep from falling because of the sudden increase in friction. And this isn't always enough. In 1989, a geomagnetic storm was so strong that it knocked NASA's Solar Maximum mission out of the sky as a sudden atmospheric increase slowed the satellite down. Ironically, the mission had been studying solar flares. This isn't a one-time thing. The North American Aerospace Defense Command, NORAD, has to move hundreds of satellites after every geomagnetic storm because they've been pushed out of their old orbits. Radiation can also affect our ionosphere, filling it with charged plasma. This can create a small lensing effect on GPS systems, making them less accurate, going from within a meter to over 10 meters. The next time you check Google Maps and it says you're a street away from where you really are, a geomagnetic storm could be the reason. Our power grids prepare themselves every 11 years for the increase in these current-causing events to prevent overload. Amateur radio fans and airline pilots see their high-frequency radio range get much smaller as radio waves are bent or even completely blocked by the more powerfully charged ionosphere. As predicted in the initial horoscope, this all leads to less reliable technology. The fact that the next solar maximum is expected to arrive soon, in 2025, makes this prediction more confident. There are some good things about this phenomenon. As space weather gets more turbulent, some parts of the world, like Canada, see more auroras dancing hypnotically in the sky. Aurora chasers report seeing them more often, from a few times a year to as many as twice a month, during the most active parts of the sun's 11-year cycle. So that's the sun's effect on space and our technology. One might think that's the end of the story. The solar cycle might affect machines, but it won't have a big impact on living things, right? If that's what you're thinking, you'd be wrong. There's a reason the rest of the initial horoscope mentioned poorer health. There's growing evidence that solar cycles can even affect ecosystems and species themselves, including humans. Some of this is indirect. When the Schwab cycle is at the solar minimum, the sun puts out less pressure through its solar winds, which, ironically, means we get less protection from our heliosphere against cosmic radiation. This type of radiation is very energetic, but thankfully rarely gets through our atmosphere for that very reason, as it's likely to be absorbed or deflected by a passing air molecule. However, just reaching the atmosphere is enough to have an effect. There is a theory, though it's still far from proven, that this extra radiation could be creating nucleation sites in the atmosphere that form extra clouds, affecting our weather. Even if that's not happening during solar maximum, the space weather hitting our atmosphere can slightly raise the global temperature, as predicted earlier. Not by a lot, it should be said, less than half a degree, and the temperature always goes back to its original state eventually. However, it's enough to be noticed by species that use temperature cues, for example, to decide when to start their mating season. Studies of birds have shown that in warmer years, they tend to lay their eggs earlier. Curiously, a study published in 2009 by researchers in the Netherlands even showed that the laying times of blue tits were affected by the number of sunspots happening, which even the researchers found hard to explain. It's not like birds can look at the sun to count sunspots. Still, a link seems to exist. according to the 5 nesting groups that were studied. This phenomenon doesn't just affect blue tits or even species like homing pigeons that are sensitive to magnetic changes and fly different routes depending on the point in the 11-year cycle. This relates to the last unmentioned point in the horoscope: compromised health. Many studies are looking into how solar cycles might influence this. In 2011, a study that lasted 2 decades and involved nearly 1/3 of women in Holland found a peak in 6 cervical pathologies that happened just after solar maximum, when the sun's radiation was most intense. The study also looked at 1 man during the same period, which is admittedly a much smaller number of subjects. Still, it was interesting to see that the man had slight increases in oral temperature, pulse rate, blood pressure, and respiration rate that occurred soon after solar maximum as well. The influence isn't just physical, there's even an effect on the rate of mental disorders. A 2006 study looked at 237,000 clients in the main Medicaid database collected between 1995 and 2004. They found that among all those clients, those born during higher energy, chaotic cycles had a higher rate of mental disorders. If this is truly the case, then the sun's cycle at the moment of one's birth might just have influenced the path of their life. It's not exactly star signs, but astrology might have accidentally found a partial truth, at least about one specific star. Ultimately, the science on this is still new, and it's important to stress that any health effects from these cycles are very small. As one researcher put it, it took hundreds of thousands of patients to even see a health impact. The solar cycle shouldn't stop anyone from living their life. We are currently getting close to a solar maximum, expected to come in 2025. However, for those who are worried, living through or being born in a solar maximum isn't all bad. The same study suggested that this radiation might lead to more creativity and adaptability. Perhaps it was during one such cycle 80,000 years ago that a human brain mutated, giving it abstract thought and consciousness. If so, if they gave us the ability to see the universe, we owe a lot of thanks to solar maximums. We wouldn't be who we are without them. What sound does the sun make? It's a simple question with a seemingly simple answer. The sun is silent, of course, because sound can't travel in a vacuum. To us, the sun makes no sound we can hear. But let's put simple answers aside. What if sound could travel through space without a giant cosmic silencer between us and our closest star? What would we hear? Would the sun serenade us with a beautiful melody in our sky, or would its noise be such a devastating roar that it would instantly be the last thing we ever heard? Scientists actually have the answer. Using spacecraft like the Parker Solar Probe, which is currently making skimming orbits around the sun, they can detect the kinds of pressure waves and particles the sun emits and turn those waves into the sounds we might hear if space could carry them. And interestingly, not all of the sun's sounds are the same. Join us as we listen to several different sounds made by the sun, recreated through clever science, because it turns out that these sounds might help scientists solve 2 of the sun's biggest mysteries. In our imaginary scenario where space can suddenly carry sound, we can now start listening to the sun all the way from Earth. Even though Earth is, on average, 152 million kilometers away from the sun, it might not be a surprise to learn that the sun is extremely loud, easily heard from where we are. It would sound something like a calming buzz with an almost electric quality, like generators, or maybe something faintly radioactive, which makes sense since we're talking about the sun. The nuclear fusion happening inside the sun is equal to 3. 85 watts 10 down twice into 26. Watts every second, about 1 million times more than what all of humanity produces in a whole year. All this generated power has a predictable cascading effect on how loud the sun would be. To understand how intense this is, imagine connecting the device you're using right now to the speakers at your next rock concert, then playing this sound at full volume. At 110 decibels dB, this volume is survivable for short periods, but would likely make the entire population of the planet deaf if they weren't wearing earplugs, as it would be playing constantly in our sky. In fact, we can consider ourselves incredibly lucky that we don't actually have to deal with this. Species would probably have evolved without ears, since hearing would be pointless. As we get closer to the sun's surface, that sound level grows exponentially, with some experts estimating it at 270 dB. Remember that dB is a logarithmic scale, so every 10 dB increase means multiplying the sound level by 10. To understand how loud this is, 270 dB is louder than our own atmosphere can physically carry. There is a limit to sound at 190 dB in Earth's atmosphere, as different mediums have different volume limits because of complex details of wave amplitude and energy levels that we won't get into here. The volume of the sun would be 100 million times higher than this limit. The sun is incredibly loud, which is a shame, because some of its sounds can only be told apart when we get into that deafening zone. By the time the sun's noise gets to us, many of its sounds have blended into one, which means we miss out on some of their fascinating details. To get a better understanding of the sun, we would need to get closer, entering that intensely loud zone of noise. So let's ignore the sun's volume for now and instead focus on its sound patterns. If we were to get on a spacecraft and fly toward the sun, we would soon start to hear a difference in the sound's consistency. Instead of a steady buzzing, we would hear something that represents the sound of the solar wind. The sun gives off a constant stream of charged particles that blasts out across the solar system, and its existence is one of the sun's biggest puzzles to date. You see, it's easy to think that this stream comes from inside the sun and blasts out with the incredible force of all that nuclear fusion. However, by the 1960s, an important discovery had been made through observation. Although particles in the sun's atmosphere, or corona, were moving around at an average speed of 145 meters per second, particles outside the corona were moving at 618 meters per second. This meant that particles with enough speed to escape the sun's surface were drifting into space, and then something in the sun's corona was hyper-accelerating them from subsonic to supersonic speeds, launching them. The exact process or mechanism for this is still a mystery today. The corona also has a second mystery: it is way too hot. Although you might expect the center of the sun to be its hottest part, with the temperature slowly getting cooler the further you move from the center, this stops being true once you get into the corona. The surface of the sun has an average temperature of 5,600 degrees Celsius, but within a few kilometers, the corona suddenly has a temperature jump to as high as 2 million degrees Celsius. Something in the sun's corona is accelerating solar wind into space, and something is causing extreme heating. Scientists also don't know why this is happening, though it's thought to be related to magnetic fields. It is here that we would find the third sound of our tour of the sun. As our spaceship got closer and we crossed the line between the corona and empty space, a region known in science as the Alfvén surface, we would start to hear what are known as Langmuir waves. They are made by tiny oscillations of plasma particles vibrated by light itself as they stream from the sun through tiny funnels on the sun's surface, a magnetic version of the sound a kettle makes when it boils. We would have entered one of these streams. Countless of these streams come from the sun's surface. The sun's outside is covered in islands of hot material rising from the star's center. Once there, the material cools and sinks back into the star's mass along the island's edge. And something about this process of rising and falling material, or something happening inside the sun itself, causes these sinking zones to give off powerful magnetic field lines. Plasma is gathered by the magnetic force and shot into space, the starting point of the solar wind. Scientists don't know what causes this process, but the sound of Langmuir waves is hauntingly beautiful. As the winds move outward, not all the waves created this way travel at the same speed. This has the effect of spreading out sounds as faster parts of the wave move ahead while slower parts of the wave fall behind, creating what are known as dispersive waves. Such waves are filled with chirps, small eddies of sound where fast waves coming from behind meet slow waves already traveling ahead. Eventually, this all blends into the hum we first heard. There is one last sound that might give us a clue to the whole mystery, one that has interesting implications. Right inside the sun's boiling corona, we can finally start to hear Whistler mode waves. Whistler waves are the distant echo of high-energy events that echo through the plasma of a celestial body's magnetosphere. On Earth, we hear them whenever lightning strikes. More than just thunder, a ripple goes through the planet's magnetosphere that can be detected kilometers away if you have the right detectors. To really understand the scale of these waves, think about what they sound like on Earth. Just a few small clicks and whistles, nothing very special. Now compare that with what they sound like on the sun, to go from sparse, short clicks to a deafening roar of wailing wind shows that the sun's magnetosphere isn't just getting an occasional lightning crack. Something is happening all the time, everywhere, blending individual moments into one constant roar. Scientists are still trying to figure out the cause of that roar, but at least one theory for the force behind the sound, which can explain the dramatic acceleration and superheating of matter in the corona, is a rather simple-sounding event called magnetic reconnection. Magnetic reconnection sounds pretty harmless, yet its seemingly innocent technical name hides a disaster. The sun is a tightly wound ball of shifting magnetic field lines, all because of the churning plasma in its core. The immense power of these fields can't be overstated. When magnetic field lines stretch away from the sun, it's sometimes possible for them to merge with other field lines, leading to the creation of some of those iconic loops often seen in pictures of the sun. However, at the moment such arcs are formed, chaos breaks out. When two parallel lines touch, making an arc, there is a huge realignment in the polarity of the extra field lines. Everything above the arc needs to find a new arrangement to make sure magnetic balance is kept. Cut off from their tethers, the field lines further out from the sun form an arc of their own, which then shoots off into space like the release of a giant stretched rubber band. This rapidly accelerating magnetic force is known as a nanoflare, and it indirectly heats the corona above it to multi-millions of degrees in seconds. Scientists have only recently developed the ability to even see nanoflares, and aren't completely sure that the nanoflares they've seen are indeed the theoretical events they were expecting, although they do seem to come with the expected superheating. This explanation is still being developed, and much of it isn't fully understood yet. Yet it's not entirely unbelievable that such moments when the sun gets so wound up it snaps explain why its corona is as hot as it is and why it's throwing solar winds across the solar system with so much force. Although, to go from a single crack to the roaring wail that we hear, and to explain the constant solar wind moving outward in all directions from the sun, nanoflares, or whatever force is behind this phenomenon, must be extremely common throughout the entire corona. The sun still holds many mysteries. The Parker Solar Probe, which recorded many of these sounds, continues its journey around the sun, collecting valuable data with every pass. The Parker probe is only 4 years into its 7-year mission, so hopefully it will gather much more information for scientists to analyze. Perhaps they will find more sounds for us, each one a clue to the ancient puzzle of how the universe works. Ironically, just like listening to the ticking of a clock to try and figure out how the clockwork operates, the secrets to the sun might one day be solved by what we hear, rather than by what we see. It is a natural human wish to be remembered. For thousands of years of human history, people have built monuments to themselves and done great things, all to last after they are gone. It's no surprise that some people might want to be the one who made a big scientific discovery, like finding a special star or a planet, so they might be remembered forever. However, being too eager could lead to being remembered for all the wrong reasons. Today we'll look at the fascinating story of a planet supposedly found in our solar system, located closer to the sun than Mercury. It was seen dozens of times by different astronomers. The only problem? It doesn't actually exist. Let's go back to the year 1846, a time when something amazing had just happened in the scientific community. Urbain Jean-Joseph Leverrier, a French astronomer and mathematician, had just played a key role in the discovery of the planet Neptune, using only pure mathematics. He had been carefully studying the rotation of the then 7 known planets when he saw a problem with Uranus. Its movement didn't match the theories of gravity proposed by Newtonian physics. Leverrier figured that the only logical explanation for this was the existence of an undiscovered planet beyond Uranus's orbit, disturbing its motion. To explain this difference, he did complex calculations and then announced that this 8th planet must be at an exact spot in the night sky. The truly amazing part was that upon hearing his prediction, Leverrier's friend, Johann Gottfried Galle, immediately got a telescope, looked at the specified location, and, sure enough, found the planet Neptune in just 1 hour. It was almost exactly where Leverrier had said it would be. The scientific community was thrilled with this discovery, and Leverrier was rightly praised for his amazing deductions. So it was not surprising that a decade later, when he predicted the location of a 9th planet using the same method, the scientific community listened carefully. To be fair, he wasn't the first to suggest the existence of such a planet. As far back as 1601, the German astronomer Christoph Scheiner had claimed to have seen a strange black spot moving in front of the sun, and said it was a planet. In reality, it was most likely a sunspot. Other supposed sightings had been made over the years: Kappelhoft in 1818, Franz von Gruithuysen in 1819, and J.W. Pastorff between 1822 and 1837 all claimed to have seen an object or objects orbiting the sun. Pastorff even said he saw it at least 12 different times. People had even started to suggest a name for this hypothetical planet. In 1846, French astronomer Jacques Babinet suggested naming it Vulcan, after the Roman god of volcanoes, fire, and metalwork. This would have been a fitting name, as any planet closer to the sun than Mercury would have been extremely hot. Mercury already has temperatures of 427 degrees Celsius. Vulcan would have been even hotter. Yet, despite all these sightings, confirmation of the planet was still missing. However, what made Leverrier's claims different was how he had come to them. In 1845, before he discovered Neptune, Leverrier had been asked by the director of the Paris Observatory to apply Newton's laws of physics to the orbit of the planet Mercury to see if the two matched. Leverrier took on this task, outlining a theoretical orbit that Mercury would follow around the sun based on Newtonian physics. Once his prediction was made, astronomers watched Mercury to see how closely it matched, only it didn't. Leverrier tried again, thinking his calculations might have been wrong. He did a much more detailed study in 1859, using multiple observed sightings of Mercury as his starting point. Once again, he mapped out Mercury's orbit, but once again his predictions were off, not by a lot, only 45 arc-seconds per century, but enough to clearly show that something strange was happening. Confident in his math skills this time, Leverrier concluded that there must be some mass pulling on Mercury, pulling it away from its ideal orbit, either a planet or a group of asteroids. Given his recent success in finding Neptune, many astronomers believed him. Scientists eagerly ran to their telescopes to try and see the supposed planet, and it wasn't long before reports started to come in. Seeing a planet so close to the sun was naturally hard. The sun's intense glare would completely wash out the reflected shine of a tiny planet. So, the best way to find such an object was to watch for the darkening it caused as it moved across the sun, and in 1859, Edmond Modeste Lescarbault claimed to have seen just that. Lescarbault was a French amateur astronomer and physician who, using simple tools in a homemade observatory, claimed to have seen a small black object pass by the sun on December 22nd. He wrote to Leverrier, who was so impressed by his claim that he traveled by train to the man's home unannounced to check it. He questioned Lescarbault, heard his observations, and decided that the man was telling the truth. So the two of them announced Lescarbault's discovery to the scientific community, naming the planet Vulcan. The scientific community was once again very impressed. Lescarbault was given the Légion d'honneur, the highest award of merit in France. He was invited to speak at meetings of respected scholars. There was only one problem. The planet he had found didn't actually exist. Many pieces of evidence proved this. For one, other scientists naturally wanted to see this new planet Vulcan. Leverrier calculated from Lescarbault's observations that Vulcan must orbit 21 million kilometers out from the sun and complete an orbit every 19 days and 17 hours. So it should be easy to see, as its transits across the sun would be predictable. Astronomers pointed their telescopes at the sun at the right time, but Vulcan didn't show up. Leverrier was bothered by this, but by then, more reports of the planet's sighting were coming in. Other astronomers were looking at their past records and connecting things they had seen with the new planet Vulcan. Some of these observations were years old and not even accurately dated, but Leverrier still used them to improve his model, thinking that maybe his calculations were just a little off. So he would predict and would not see Vulcan, and would fix his theory, and would still not see it again. Another damning piece of evidence came from Emmanuel Liais, another French astronomer. Liais claimed that he had happened to be watching the sun at the exact same time as Lescarbault with a twice as powerful telescope, and had not seen the planet Lescarbault had claimed to see. Vulcan's existence remained in a gray area, as famous scientists sometimes claimed to see it. Leverrier died in 1877, but just a year later, in 1878, two well-known astronomers both claimed to have seen Vulcan at the same spot in the sky at the same time during a solar eclipse. They even both said that the planet was reddish in color. The matching stories were convincing, yet Vulcan still did not exist. In science, if a fact is true, then it can be repeated, and despite all these sightings over the years, Vulcan was never consistently seen. It was never seen again during a solar eclipse. In time, that matching sighting was blamed on calculation mistakes and the misidentification of a known star. But in the end, the person who finally put the idea of Vulcan to rest was Albert Einstein, and he did it by thinking of something completely different. Many scientists over the years had tried to find Leverrier's hypothetical planet Vulcan because, mathematically, they were sure it had to exist. Newtonian physics required it. They tried hard to see it, and in that confirmation bias, they did see it again and again, just never in the same place. But Einstein realized that Newtonian physics itself was wrong. In 1915, he proposed a model of physics that accurately described the motion of the universe, but used concepts like the curvature of space-time instead of gravity. At slow speeds, it looked a lot like Newtonian physics, but when objects like Mercury were put next to very massive objects like the Sun, special relativity predicted a different path for their orbits. And indeed, Einstein's model perfectly predicted the exact orbit that Mercury followed around the Sun, differences and all. With that, the case for Vulcan's existence disappeared. Under special relativity, it could not exist. There could be no object of planetary size near the Sun, or it would mess up Mercury's orbit, so that it would no longer match the calculations. And this time, Einstein was able to prove his calculations were right through tests like the Eddington experiment. There is a lesson to be learned here. Sometimes, if we want something too much, we find it, whether it's really there or not. Sometimes it takes thinking outside the box and questioning our old beliefs before the truth can be found. As scientists, and just as regular people, it is important that we don't hold on too tightly to our preconceived ideas. The truth doesn't need our strong belief. It will prove itself with time and chances for repetition. So there you have it, the planet Vulcan, a planet of fire that was nothing but smoke and mirrors. A wish for something that never became real. Newtonian physics was replaced by Einstein's theories of relativity, and now special relativity is here to stay, at least until it is replaced by something even more complete. Have you ever looked at the sky and seen something so strange it made you doubt your own eyes? Maybe you saw what looked like a rainbow, but it was upside down. Or maybe you saw a perfect circle of light around the sun with two splashes of rainbow color on its sides. Well, there's no need to pinch yourself. What you were seeing is a special category of optical phenomena called ice halos. Although similar, they are not technically rainbows, but their own unique wonder. Some are fairly common, while others are extremely rare. As you may know, rainbows happen when sunlight is bent by water droplets hanging in the atmosphere. When light goes from one clear substance to another, like from air to water, its speed changes, bending its path and separating the light into colored bands by wavelength, a process called dispersion. But what happens when light hits water particles made of ice instead of liquid water? Depending on the shape and orientation of the ice crystals and the direction of the light hitting them, they can create a whole range of optical phenomena. To date, 119 types of ice halos have been categorized, and there might still be others yet to be found. So, what exactly are ice halos? How do they form, and what should you look for to see one for yourself? And finally, are they a bad sign of something more threatening on the horizon? Join us today as we look at amazing pictures of some of the more well-known ice halos and solve the mystery of how and why these delicately beautiful sights appear. This amazing photograph shows a 20-second solar halo seen over Gross-Kotzenburg, Germany. The 20 seconds doesn't refer to temperature, but to the angular radius of the halo. To picture this, imagine drawing a straight line from a spot on the halo to the observer's eye, then doing the same from the sun, the circle's center, to the observer's eye. The angle between these two lines of sight is 20 degrees, which is why it's called a 20 degrees halo. There are also 46 degrees halos, which, as you might guess, are bigger than their 20 degrees counterparts, but also fainter. Halos can also appear in moonlight, as seen here. These hauntingly beautiful halos are called moon rings or winter halos, but they are technically the same optical phenomenon. What makes them different from solar halos is the light source. In some pictures, you might notice that the patch of sky inside a halo looks darker than the sky outside the ring, a dramatic effect sometimes called a hole in the sky. This happens because when light bounces and bends off the ice crystals, none of it is reflected toward the light source, which, to an observer, leads to a seeming darkening inside the halo. But this is just the beginning, because ice halos take on all sorts of strange and amazing forms: bright spots of color, upside-down rainbows, and even upside-down rainbows at night. But before we go on, let's take a moment to break down the fascinating optics that create these strange events. Most circular halos are formed by water crystals in cirrus or cirrostratus clouds. These clouds are high in the troposphere, usually 5 to 10 kilometers above Earth's surface, where temperatures are very cold. As a result, halos can be seen anywhere on Earth all year round, even in very hot places. Atmospheric ice crystals are small, usually less than 10 micrometers long, and uniform in size and shape. This extreme regularity is because of the molecular structure of ice and is key for halo formation. You see, water molecules are made of 2 hydrogen atoms and 1 oxygen atom. In liquid water, the bonds between hydrogen atoms are weak, always breaking and reforming as the molecules slide past each other. But when water freezes, that molecular movement stops, and the bonds between hydrogen atoms become fixed. This creates a hexagonal lattice structure known as a tetrahedral arrangement. This highly organized structure at the molecular level is what makes the ice particles form hexagonal crystals. Some crystals are flat like plates, while others look like columns with a hexagonal cross-section. Despite this difference, these crystals act so uniformly because of their interfacial angles. In fact, the angles between any 2 faces of ice crystals are exactly the same. It is this extreme regularity of the interfacial angles, not the crystal's mass or shape, that lets millions of particles scatter the light with the consistency needed to make a halo. Halos are sometimes quite colorful because when ice crystals bend light, the red and blue frequencies bend at slightly different angles and spread out. Some 20 Sagades halos have 2 colorful spots visible to the left and right of the sun. These beautiful phenomena are called parhelia, or sundogs. Sundogs appear when ice crystals shaped like hexagonal plates take on a horizontal orientation. As mentioned before, some crystals form as thin hexagonal plates, while others form as columns with a hexagonal cross-section. When plate-shaped crystals form and fall, atmospheric drag orients them horizontally, with the c-axis almost perfectly perpendicular. Larger plates tend to wobble a bit more than smaller ones. This wobble, in turn, affects the apparent height of sundogs, with wobbling plates making the sundogs look more vertically stretched. Sundogs are sometimes joined by another optical phenomenon called a circumzenithal arc. These arcs look like rainbows, only they are upside down, giving them a friendly, smiling look. These arcs appear above the sun only when the direction of light and the orientation of the ice crystals are just right. When light enters the top faces of hexagonal plate crystals and leaves the side faces. However, this can only happen when the sun is lower than 32.2 degrees above the horizon and more than 5 degrees. Because the ice crystals basically act as a 90-degree prism, the color separation is excellent, meaning circumzenithal arcs have a much higher degree of clarity than real rainbows. And if you are really lucky, you might even see one with moon rings known as lunar circumzenithal arcs. These unusual arcs only appear when the moon is very bright and relatively low on the horizon. As strange as it sounds, it is indeed possible to see what looks like an upside-down rainbow at night. This is truly amazing. Circular halos have also been seen on Mars. Here is a picture taken by Perseverance on December 15, 2021. This has led some to suggest that the cause may be carbon dioxide crystals in the planet's cold, thin atmosphere, or maybe a mix of CO2 and water ice. We didn't always know that halos happened on Mars, so as you can imagine, the Perseverance team was quite excited to see this, because the size and look of the halos give clues about the types of crystals forming in the atmosphere. Scientists hope that studying halos here on Earth and seeing them on other planets could shed light on the composition of those planets' atmospheres. As a result, more research will be done in the future to document and understand the appearance of ice halos on Mars, as well as other moons and planets. So there you have it, a basic guide on some of the more well-known ice halos and their related optical phenomena. And if you want to see one for yourself, here are some things to look for. First, check for cirrus clouds. These are the high-altitude wispy clouds that have the small ice particles needed to make ice halos. Second, look for the sun or moon, but be careful not to stare directly at the sun, as that can hurt your eyes. While rainbows form around the anti-solar point, which is located directly opposite the sun in the celestial dome, most ice halos form close to the sun or moon. And while ice halos tend to appear in fair weather, they often come before an approaching storm system, meaning if you see one, it's a good idea not to stay outside for too long. Head inside, take a break, and find somewhere cozy to enjoy the coming storm. So if the weather is fair but rain is in the 24-hour forecast, keep an eye on the sky. Your chances of seeing a halo will be higher. Of course, the best way to see one is to look every day. Ice halos can form anywhere on Earth, so if you keep looking up, you are sure to see one sooner or later. But when it comes to ice halos, there's much more to talk about. There are many other strange and even rarer types of halos, and probably more yet to be discovered. The Solar and Heliospheric Observatory, SOHO, recently celebrated its 25th anniversary in space. During these 25 years, it has carefully watched the solar wind, monitored for dangerous coronal mass ejections, CMEs, and studied the sun's atmosphere. An unexpected result of its observations in this region was the discovery of over 4,000 sun-grazing comets, most of which were completely unknown until they entered SOHO's field of view. And SOHO is not the only solar observatory. The Stereo spacecraft and the Solar Dynamics Observatory have all found new comets, and what's amazing is that they were not designed for this purpose at all. In this video, we wanted to look at some of the most impressive of these comets, trying to understand how they interact with the sun and how the sun in turn interacts with them. Sun grazers are comets that, as their name implies, graze the sun as they pass, with the closest parts of their orbits bringing them within a whisker of the sun's surface. Often they will travel through the sun's huge atmosphere known as its corona. These comets are mostly long-period comets whose orbits take hundreds to thousands of years to complete. Because of the extremely elliptical shape of their orbits, they build up tremendous speeds as they get close to the sun, sometimes accelerating to 0.2% of the speed of light, an absolutely incredible speed for a particle, let alone an object the size of a house. Most sun-grazer comets actually come from one giant comet that broke apart several hundred years ago. This group of sun-grazers, shown in red in this video, is known as the Kreutz sun-grazers. What usually happens over time is that the pieces from the larger comets spread out, which means a continuous stream of them. As the largest of these comets also pass by the sun, they too break up into even smaller comets. The reason we think most sun grazers come from the same comet is that they all tend to follow the same orbital path. the brightest comet in the last millennium, known as Comet Ikeyaseki, was likely a piece. It was so bright as it got close to the sun that it could even be seen during daylight hours. You may have heard of another famous piece of this comet that dimly lit up the sky in the southern hemisphere in 2011, called Comet Lovejoy. While Comet Lovejoy was not as bright to the naked eye, it gave us some very impressive long exposure pictures and was seen by all the sun-observing satellites. Comet Lovejoy was not expected to survive this meeting, as it would have been within the sun's 1 million degrees Celsius corona for over an hour. However, amazingly, it came out from the other side of the disk mostly intact, though likely severely affected by the experience. The same thing happened to another comet, Comet Ison. You may remember that Comet Ison was expected to be a bright comet, possibly visible to the naked eye, when it passed by the sun in 2013. Sadly, that was not to be. Still, it gave excellent viewing for the sun-observing satellites. Ison's approach was bright and impressive, and when it got to the other side of the sun, it faded out. Scientists can't be sure if the nucleus survived or not, but if it did, there are certainly no volatile substances left on it. All that is left is probably dust. However, these are some of the largest Kreutz sun grazers we have ever seen, their nuclei perhaps being a few hundred meters in diameter. Some of the smaller comets were unknown until they actually came into the view of a sun-observing satellite because of their small size, being only tens of meters across. Many of the smaller comets were completely destroyed by the sun immediately after passing by too closely, which unfortunately means they were vaporized almost immediately after they were found. Sometimes they will pass behind the disk of the sun, never to come out from the other side, although at other times the angle of the comet's orbit lets us see this vaporization as it happens. At this distance from the sun, the heat is incredible, and the gravity is overwhelming. The icy comets not only evaporate quickly, but their rocky parts are also torn apart by tidal forces. Our own close encounters with comets show that they tend to be structurally weak and very porous, sometimes nothing more than a pile of rubble held together by its own gravity. So, combine that with the sun's influence, and even the largest sun-grazer comets will come out heavily scarred. Now, an interesting thing happens when a sun-grazer passes by the sun. A CME will erupt at the exact moment the comet passes. There are many examples of this. However, scientists still believe that there is no way for a sun-grazer to cause a CME. These comets are simply not big enough to have any major impact on the sun. So it is currently thought that these examples you see are purely coincidental. What scientists like about sun-grazers, however, is that while we can't send probes deep into the sun's corona, it is simply too hot for that, we do have these thousands of comets that are willing to take the plunge for us. And comets are perfect for seeing what we want to see, a better understanding of the magnetic fields within the corona, so that we can more accurately predict CMEs and space weather in general. Notice how, as a comet passes, its tail wiggles. The particles in the tail get so hot they turn to plasma, which is easily visible to the satellite's UV cameras. Plasma reacts strongly to magnetic fields, so the wiggle seen in the tail is thought to be because of the way the tail interacts with the magnetic field lines in the corona. Currently, space weather is something we don't completely understand, so as more comets pass through, the more we will begin to understand that environment. So, there you have it. Some of the most impressive-looking sun grazers caught on camera by satellites that were not even designed for them. Have you ever wondered what it would be like to have two suns in our sky? Seeing two suns during a sunset would surely be a stunning sight, and in fact, it's not that uncommon. It's currently estimated that a third of star systems have two or more stars, which brings up the question, how much would a second star affect us here on Earth? How hot would Earth get? What would the day and night cycle be like? Would it be possible for life as we know it to survive in a multi-star system? Well, it depends. Let's keep our sun as it is, and let only the second star be the variable in this thought experiment. As we know, stars vary a lot in size, from small, cool, and dim red dwarfs all the way up to large, hot, and bright blue supergiants. In a binary star system, the stars orbit around the system's barycenter, or the center of mass. Depending on the mass of the stars and the distances between them, the look of these orbits will be different. For similarly sized stars, the orbit could look circular or elliptical. On the other hand, the bigger the difference between the stars' masses, the closer the barycenter will be to the more massive star. Let's imagine we put a red dwarf, which can be as little as 7.5% the mass of our Sun, in a close orbit around our Sun. Even with this relatively small mass, it would already have a big impact on us. From our point of view, the star would seem to orbit the Sun, which means there would be times when it passed in front of the Sun and other times when it was hidden by the Sun. Our year would be shorter if we kept our distance of 1 astronomical unit from the system's barycenter because of the increased mass and gravity of the system from the extra star. Earth's speed would have to increase to avoid being pulled into either star, or its orbit would need to be a bit further out if we wanted to keep our current speed. The temperature increase from the second star would also be noticeable, definitely making it unbearable for humans. However, the exact temperature would depend on various things, such as a runaway greenhouse effect, the heat of the star, and more. But let's assume we put Earth's orbit in a place where we can survive. Seasons would still be massively affected, as the planet's tilt would be less important than its distance from the second star. When the second star is as far away as possible, and the hemisphere on Earth was also having winter, it would get extremely cold. On the other hand, combining a summer with the second star passing as closely as possible would lead to incredibly high temperatures. Also, a strange thing about red dwarfs is that they also make huge flares, much bigger than those from our Sun. These would easily knock satellites offline regularly, and Earth would have spectacular auroras. Our power grid, as it is now, would also be under serious threat from these stellar flares, as they would act like hemisphere-wide EMP bombs. The interactions with this second star could also make our Sun more active, meaning it too might make more flares. So even with the smallest type of star, our ability to live on Earth would be in serious danger. Increase the mass of the second star, and more problems would start to appear, such as increased UV radiation, making going outside more and more dangerous. You would also often see two shadows. Once you change the second star into something like a blue supergiant, there would truly be no place in the system where there is even a small hope of life. Blue supergiants can have many times the mass of our Sun, with the theoretical limit being 150 solar masses. Their volume is also huge. They make the Sun look almost tiny in comparison. They can be millions of times brighter than our Sun, too, with devastating stellar winds strong enough to strip away our atmosphere over a relatively short time. Even bigger are yellow supergiants, and then red supergiants. While not as massive or as bright as blue supergiants, red supergiants are the largest stars in existence. If you were to put the largest known of these stars in the center of our solar system, not only would it easily swallow Earth, but it would engulf everything up to Saturn. That's 10 billion times the volume of our Sun. However, there is a situation where we could exist in a binary star system with a supergiant and still live on a habitable planet. You see, binary stars can orbit very far apart, taking thousands of years to complete one orbit. The most extreme cases can have a binary star system with a separation of over 1 light year. And what can happen is that planetary systems form around each of these stars separately, meaning that if Earth were in one of these planetary systems, it would only have one parent star, even if that star were part of a binary. The second star would be easily seen in the night sky but might not have much impact during the day, depending on how bright it is. Stellar winds from the other star would have little effect on Earth, as our sun's powerful magnetic field would redirect most of it away. The major problem with a supergiant at our doorstep is that it is a ticking time bomb. Supergiants tend to be about to erupt in a supernova. A supernova happening only 1 light year away would be catastrophic, likely sterilizing the entire planet as radiation from the shock wave passes over, not to mention the gamma ray bursts from the resulting neutron star. In fact, a recent study has suggested that being within 50 light years of a supernova explosion would be close enough to be catastrophic. However, the good news is that we are not aware of any star capable of erupting in a supernova within 100 light years. Going back to the single-parent star binary star setup on Earth, with a single sun, we have a set day and night cycle. However, if we had a second sun outside our orbit but still relatively close, it would significantly mess up our day and night cycle. There would only be tiny parts of the year when you would have a proper day and night cycle. And as the year went on, you would have less and less night until a point where there would be no night at all. So, there you have it. While the idea of seeing a second sun during a sunset might seem amazing at first, looking into the details shows that we are extremely lucky to have only one sun. No matter what setup you think of, there are big problems with a second star, be it devastating solar flares, a ruined day-night cycle, having a neighbor that might explode at any moment, our orbit being completely consumed by the star's volume, huge swings in seasonal temperature changes, our electronics being regularly fried, UV radiation, and likely more unmentioned issues. In reality, even if life as we know it does exist around binary star systems, they face major hurdles to reach our current stage of development. So let us be grateful for our seemingly boring but steady and safe star, the Sun. May it continue to be so for a long time. Often, on a clear day, one might take a quick look at the Sun and be filled with wonder at its immense size and brightness in our sky. It's hard to grasp that it is millions of kilometers away, yet it has such a deep impact on us here on Earth. Life would be impossible without the Sun. Almost everything can be traced back to the light and energy it gives us. Even though it's relatively close to us and not particularly hard to see, there's still a lot we don't understand about it. This is why both NASA and ESA have sent spacecraft to study the Sun within the last 2 years. These missions will bring us closer to our star than ever before, so close, in fact, that they will be able to directly interact with its atmosphere. So why are we sending these spacecraft to the Sun? What will they do there? What have they found so far? And what makes each of these missions special and unique? In this video, we will look into NASA's Parker Solar Probe and ESA's Solar Orbiter and how they will explore our own magnificent star, the Sun. A total solar eclipse happens when an object passes in front of the Sun, completely blocking it. This phenomenon is also known as an occultation of an object. This is the typical kind of eclipse we see on Earth when, at certain points in Earth's orbit, the Moon's orbit lines up with the Sun. There is something truly special about an eclipse here on Earth, and this isn't just an expression of Earth-centric pride. By a strange but very lucky cosmic coincidence, the Moon has the exact size and distance from us, such that its angular diameter in our sky is almost identical to the angular diameter of the Sun. This creates an impressive sight, where the corona of the Sun, or in other words, the sun's upper atmosphere forms a ghostly halo around the moon. This corona, normally too dim to see, extends for hundreds of thousands of kilometers into space. Looking closely around the edge of a total solar eclipse, one can also see the silhouette of the moon's craters along its edge, plus reddish wisps coming from the sun. These are prominences, millions of tons of charged particles suspended in the sun's atmosphere by powerful magnetic fields. During an eclipse here on Earth, the moon casts a shadow about 250 kilometers in diameter, which moves across the Earth as the moon orbits. In the case of the eclipse happening this April, 2024, this shadow will arrive at the Mexican west coastline, then go through the United States until it passes into parts of Canada, before moving over the ocean once more. You can see the path the shadow will take on this map. If any of you happen to live within its path or are close enough to drive, you may want to try to see this eclipse for yourself. The sun will only be totally hidden within the diameter of the shadow. Outside of that, the sun is only partially hidden from the viewer's perspective. This viewer is seeing an annular or partial eclipse, also known as a transit. The shadow moves across the Earth very quickly, at roughly 1 kilometer per second. Seen from a high altitude, it's a majestic sight as the shadow moves across the landscape. Satellites have also seen the movement of this shadow. The shadow is not as sharply defined as one might think, and this is because of the angular diameters of the sun and the moon, and their respective distances. The sun itself is enormous, a huge 1.4 million kilometers across. The moon is much smaller, at only 3,400 kilometers across. Now, this image is not to scale, but it visually shows why the shadow is not sharp. The umbra is the shadow where the sun is completely hidden, and the penumbra is the shadow where the moon only partially hides it. This part of the shadow is much wider than the 250-kilometer wide umbra shadow. So, why doesn't the moon create eclipses every month when it orbits in front of the sun? This is because the moon's orbit is not aligned with Earth's orbit around the sun. This means there are only a couple of times per year when the alignment is correct. This alignment of three celestial objects is known as a syzygy, a very cool word, but not something you'll need to remember for this video. It's just an interesting fact. If you live in the UK, you sadly will not get to see much of the eclipse this April, unless you live in the westernmost parts of the country, as the sun will be going below the horizon just as it starts. Perhaps some devil's horns might be visible, still a spectacular sight indeed. But Earth is not the only place to experience solar eclipses, and we have pictures and videos to prove this. Let's look at eclipses involving our closest celestial neighbor, the moon, because it would logically follow that if the moon can occult the Earth, then surely the Earth can occult the moon. And the answer is yes, but it is not the shadow itself that is truly visually appealing from Earth's perspective. This is because the Earth is 4 times as large in the moon's sky as the moon is in Earth's sky. So when the Earth fully hides the sun, the entire moon is within the umbra. Initially, the Earth's shadow creates a crescent shape. But what is different in this situation is that, unlike the moon, the Earth has an atmosphere. This means that when the moon is totally eclipsed, the Earth's atmosphere reflects the sun's light around the planet, gently lighting up the moon in a reddish color. This creates a beautiful but almost eerie view. The color is caused by Rayleigh scattering, the same process that makes our sky blue and our sunsets red. This image is beautiful in that you can see the different wavelengths of light being scattered through Earth's atmosphere, from deep red on this side through to blue on this side. From the moon's perspective, none of the sun would be visible during a total eclipse, but the atmosphere on Earth would be lit up, so one would see a ring around it. This is an actual view of a lunar eclipse on the moon taken by one of the JAXA probes in 2009. It is quite a stunning sight. The Earth and Moon are not just blocking each other's views. Here is the Earth eclipsing the Apollo 12 spacecraft in 1969 while it was on its way back, and here is the Moon blocking the Earth from the perspective of the DS-GOVR satellite. Interestingly, this is the side of the Moon you never see, as the Moon is tidally locked to the Earth, meaning the same face always faces Earth. From this perspective, the Moon looks very alien, but it is indeed a real video of our only natural satellite transiting the Earth from another satellite's perspective. But this time, watching the Sun with the SDO satellite, the Moon often appears. The position of this satellite as it orbits the Earth means the Moon can sometimes block the Sun. And here's the Moon again, this time from the perspective of one of the stereo satellites. The Moon is not the only object that orbits between us and the Sun. Mercury often transits across the Sun, a tiny fish compared to the solar system's giant. The next time this will happen is on November 13th, 2032, so a little while away. You might consider marking your calendars. Venus also orbits between us and the Sun, and as it is much closer to us and larger than Mercury, its silhouette looks much larger. Its last transits were in 2004 and 2012, but sadly, if you missed those two chances, it is very likely that you will never see it. These transits happen in pairs, and then there is a 100-year gap until the next one. In other words, the next transit will be in 2117. This happens for the same reason the Moon does not eclipse us every month. The orbits simply do not line up frequently. Still, we have high-definition videos of the last one, and it is quite a sight to see. Moving to another planet, we can go to Mars, which has numerous unmanned robotic missions, either in orbit or on its surface. Mars also has two moons, Phobos and Deimos. They are both quite small. Phobos is 22 kilometers across, and Deimos is only 13 kilometers across. However, they both orbit very close to the planet. Phobos is only 9,000 kilometers above the surface, and Deimos is 23,000 kilometers, meaning that although tiny, they're still easily visible from the surface of Mars, especially Phobos. The Curiosity rover was able to capture a moment where, incredibly, Phobos eclipsed Deimos. This video is captured in real time and shows the size differences of the moons in the Martian sky. And this is not all the Curiosity rover captured. It also saw a transit of Phobos in front of the Sun. Because of how close Phobos is to Mars, it moves across the sky fairly quickly, taking only about 7 hours to complete one orbit. This means that this video you're watching is in real time, and these solar eclipses on Mars last for no more than about 30 seconds. The surrounding ground does get noticeably darker during an eclipse by Phobos, as can be seen from the rover's perspective. But it can also be seen from space. Phobos's shadow can be seen here by the Viking 1 orbiter, and also here, more recently, by the Mars Global Surveyor. The Opportunity and Spirit rovers have also seen a transit of Deimos, but it looks much smaller, just a dot passing in front of the Sun, and it does not cause a noticeable decrease in brightness. Mars is quite impressive, but that's not all the solar system has to offer. Have a look at this video captured by the Hubble Space Telescope, focusing on Jupiter. Jupiter has 4 large moons, 3 of which can, at certain points, transit the planet at the same time, casting 3 large shadows. The moons in question in this video are Io, Callisto, and Europa. Interestingly, as we discussed before with the Umbra and Penumbra, you can see that because Io is the closest to the planet, its shadow is the sharpest, whereas with Callisto, the furthest away of these 3 moons, the Penumbra is much larger. resulting in a blurry shadow. And in this video, Hubble sees the occultation of Ganymede, the largest moon of Jupiter. We have seen some incredible transits and occultations of Saturn's many moons. Here is one of Epimetheus passing in front of Titan, with Dione entering from the side. This small white dot entering from the left, just below the ring, is in fact a bright background star, and this Hubble view is magnificent. Here are Enceladus, Mimas, Dione, and Tethys orbiting Saturn. Once every 15 years, Saturn's rings and moons align just right so that the moon shadows stream across the rings as well as on the planet. This video is a time-lapse that lasted 9.5 hours. Simply amazing. Venturing a bit further out, we encounter Neptune and its largest moon, Triton. Regrettably, we do not have a video, but this image captured by Voyager 2 is gorgeous. 3 days after passing by Neptune, Voyager was able to capture the presence of Neptune and Triton before Neptune moved in front of Voyager's view of Triton. Moving even further out, we arrive at the furthest celestial object explored in the solar system, Pluto. As New Horizons whizzed by Pluto in 2015, it turned its camera back towards Pluto to capture the dwarf planet, totally eclipsing the sun. What it saw was dazzling, the sunlight streaming through and illuminating the atmosphere and its haze layers, with the ridges and mountains on Pluto's surface highlighted by the stark contrast of Pluto's night side. Occultations and transits may be breathtakingly beautiful, but are they actually scientifically useful to us? Well, did you know that Uranus was discovered to have rings because of an occultation of a background star? As the planet passed in front of the star from our perspective, the star dimmed both before and after the planet hit it. With this information, we were able to count how many rings Uranus has. Furthermore, the transits of exoplanets in front of their stars are actually how we can detect exoplanets. Telescopes like Kepler and TESS measure the brightness of stars in the sky. If a star dims, it could be because one of its planets just passed in front of it. If the star continually dims in a pattern, for instance, once every 100 days, then we know that a planet orbits that star and takes 100 days to do so. Using this method, space agencies like NASA have discovered over 3,000 exoplanets, more than all other methods of exoplanet detection combined. It can even help scientists calculate the size of the planet by measuring how much the star dimmed, or the composition of that planet's atmosphere by examining the spectra of the light that passes through from the star to us. It might be some time before we see a solar eclipse again after the one in April. The next eclipse will not happen in America until 2044. Here in the UK, the next one will not happen until 2090. If one lives to see it, one will be a very old person. But it is amazing to see all the images of eclipses that happen throughout the solar system. There is a special beauty to each of them, a fleeting moment where one celestial body lightly touches another, even if it's only through their shadows. Rather than signs of doom, these moments inspire awe and serve as a reminder of how connected the universe is, even across thousands, millions, or even billions of kilometers of space. We can see a planet's passing, and if you're in the right place at the right time, what wonders you can behold. Earth faces a pollution problem. There are plastics and landfill items, the kinds of things one might throw away at home. And then there is hazardous industrial waste, like nuclear byproducts, biohazards, and chemical toxins. These substances harm ecosystems and negatively affect the health of vulnerable communities around the world. So far, the best solution we have for getting rid of nuclear waste is burying it deep underground. Not ideal when you consider that the material stays dangerously radioactive for tens of thousands of years. So why not just attach it to a rocket and send it into the sun, like firing a missile at a target? Wouldn't that solve all our problems? A big thanks to all of our patrons for making this series possible. If you want to send us your questions, join our Patreon by clicking the link in the description below. To start answering our question, it's actually incredibly hard to crash anything into the sun. Let's look at this more closely. Suppose we have a big pile of toxic waste meant for the sun. The first problem we would need to solve is how to get it into space. Easy, right? We've been launching things into space for the better part of a century. To push our waste payload through the atmosphere and beyond Earth's orbit, we need to speed it up to a velocity of 11.2 kilometers per second. This speed is known as the escape velocity, where the kinetic energy of the payload is greater than Earth's gravitational potential energy. Once free from Earth's orbit, our garbage craft is on its way to a solar collision, right? Wrong. Once our package escapes Earth's orbit, it is still gravitationally tied to the sun. Simply put, Earth and everything on it is moving sideways relative to the sun at 30 kilometers per second. This sideways motion, combined with the gravitational pull of the sun, is what keeps our orbit. If the sun were to somehow lose its gravitational pull, we would fly right past it at 30 kilometers per second and keep going. If we on Earth were to lose our sideways motion, we would only be affected by the sun's gravity and fall directly into it. So there's still hope for our garbage ball. How could we lose our sideways motion to make this solar freefall happen? Well, there are two choices. The first choice is to bring up enough fuel to brake in space. Now, technically speaking, you can't really brake in the vacuum of space, but the next best thing would be to set up our garbage payload's propulsion system to create thrust opposite to its direction of sideways motion. This works against the sideways motion, slowing the spacecraft down and letting the sun's gravity take over. Earth orbits the sun at 30 kilometers per second, so to brake a garbage rocket launched from Earth, you would need to be able to accelerate 30 kilometers per second in the opposite direction of its movement. Here's where it gets strange. The closer you are to the sun, the harder it is to crash into it. Let me explain. The closer you are to the sun, the faster your orbital velocity. Mercury orbits at a dizzying 48 kilometers per second, while Pluto moves at a mere 4.7 kilometers per second. The faster your orbital velocity, the more you will need to slow down to free fall into the sun. That is why it is actually much more fuel efficient to travel to the outer solar system, slow down, and free fall into the sun from there. It is not impossible to accelerate a spacecraft 30 kilometers per second. NASA's Parker Solar Probe accelerated beyond 176 kilometers per second, making it the fastest human-made spacecraft ever. But this brings us back to the problem of fuel. To make this brake and fall method work, you would first have to launch your garbage payload into orbit with Earth, then launch the fuel for the journey into orbit. Once both parts are orbiting Earth, you can fuel up your payload and accelerate it past Earth's orbit into orbit around the sun. Then you would have to use the rest of the fuel to slow down so that it free falls into the sun. Why not launch both the payload and fuel at the same time, you might ask? Well, the problem is that it is simply too much fuel. For context, the Saturn V rocket that took humans to the moon needed 2 million liters of fuel just to leave Earth's orbit at 11.2 kilometers per second. A mission like this would need orders of magnitude more fuel. No modern rocket technology would even come close to being able to carry the amount needed for such a journey. Okay, so scenario 1 is out. What other choices do we have? Another way to slow down in space is with a gravity assist. Usually when we talk about gravity assists, we mean the kind that slingshot the Voyager probes into the outer solar system. However, gravity assists are not only used to speed up probes, they can also slow them down. If you were to approach a planet from behind, fly in front of it, and leave behind the planet in a specific path. Your spacecraft would lose energy while the planet would gain energy. The Messenger and Bepi-Colombo probes have both successfully used this gravitational assist technique to lose velocity and enter orbit around Mercury. The catch is that this takes a very long time. Bepi-Colombo was launched in 2018 and will only arrive into orbit around Mercury in 2025. Surprisingly, its path to reach Mercury is longer than the distance between Earth and Pluto. This is because to slow down enough, one gravitational assist will not be enough. In fact, Bepi-Colombo needs 9 different gravity assists to slow down enough to orbit Mercury. Similarly, crashing our garbage into the Sun is all a game of carefully calculated orbital mechanics. If we don't slow down enough, we will stay trapped in the Sun's orbit. If we slow down too quickly, we might get caught in another unwanted orbit. Okay, you might be thinking, but this is all possible. It's hard, but it's within the realm of possibility. So why don't we just do it? Possible, yes. Worth the time, effort, risk, and technical challenges? Probably not. Without being cynical, think about what could go wrong. First of all, we are proposing packaging a lot of nuclear waste, biohazards, and plastic onto a rocket and launching it from Earth. A launch failure or explosion could be disastrous, to say the least. Even the world's most successful rocket, the Soyuz, has a 2 to 3% failure rate. One might not be comfortable with those odds when nuclear waste is involved. Even if the launch goes smoothly, the project itself would be ridiculously expensive, so much so that no rational person would approve the budget. There are far too many other missions on the table that would bring much more benefit to science and humanity than a garbage disposal mission. And lastly, it would actually be easier, quicker, and less expensive, though still incredibly costly, to throw our garbage out of the solar system towards interstellar space. It would be less fuel-intensive, since the acceleration needed to escape the Sun's gravitational pull is 42. 1 kilometers per second, just a 12.1 kilometers per second acceleration from its orbital speed. So there you have it. We do not launch garbage into the Sun because it is extremely difficult, highly risky, and prohibitively expensive. We are likely better off being more mindful about what we consume and how we recycle it. Earth is facing an energy crisis. Fossil fuels are limited, yet they make up 80% of our electricity source. Inevitably, at some point, we will run out of them, at which point we will either need to get our energy from other sources or get ready for the shocking reality of a world without machines, computers, and phones. If the idea of working all day with a plow in a farming society doesn't quite fit with one's life goals, then embracing alternatives for society's energy needs becomes attractive. While options like wind, geothermal, or tidal power are often talked about, do these ideas envision big enough solutions? Could the answer to the energy crisis actually be something that science fiction writers have been thinking about for over 60 years? Could humanity one day build a Dyson sphere? And how far are we from doing this? Join us today as we look at the case for Dyson spheres and find out how the mathematics behind these giant structures might make them not only possible, but actually plausible for our future energy supply. Recently, while going through an online course, the topic of Dyson spheres caught my imagination. Dyson spheres are truly amazing. They were first explored in a paper by the British-American theoretical physicist and mathematician Freeman Dyson, who was thinking about how hypothetical alien civilizations might try to power their societies and how we might find them. All life needs energy to survive, and the more advanced a society, the more energy it seems to eventually need. Dyson guessed that if an alien race were spacefaring, they might build habitats in space near their local star to use its solar radiation. Over time, more and more habitats would be built until one day, most or all of the star would be covered by a truly huge shell of habitats which would capture and use all the radiation the star was giving off. This shell was eventually thought of as a single, unified structure and came to be known as a Dyson sphere. Making one would give a species access to an amazing amount of energy, pushing their civilization into the next stage of galactic exploration and expansion. Dyson got inspiration after reading a science fiction novel called Star Maker, a source he publicly admitted, and indeed, this concept does sound a bit like something from science fiction. It would be incredibly hard, and possibly take a very long time to build anything of such a huge scale, seemingly far beyond what our current civilization can do. Still, this science fiction concept might be worth a closer look. As the course pointed out, there are just over 8 billion humans on Earth right now, and we together use 4x1020 joules, or 400 quintillion joules of energy per year. This sounds like a lot, especially when you think that the current estimated amount of remaining energy available in oil reserves is 610 × 22 joules, or 66 sextillion joules. Doing a simple division shows that we only have 150 years of oil reserves left if we keep burning it at our current rate. 150 years is not a very long time, and given the fast acceleration of global energy use, it's reasonable to think that we might run out of oil sooner. Even if more oil reserves are found, this is why finding another mass source of energy, like using the energy available in sunlight, is quite attractive compared to what we get from fossil fuels. The sun makes an amazing amount of energy, even when thinking only about the light that directly hits our planet's surface. Let's use a simple equation to show this. At this distance, the energy we get from the sun is about 1,360 joules per square meter per second. Multiply this across the approximately 1.1 x 10^14 square meters of the sun's circular area as it cuts through space, then multiply this again over the course of a whole year, all 31,536,000 seconds of it, and we would get around 4.7 x 10^24 joules of energy. That is 10,000 times the energy we are currently using from oil, more than enough to cover our needs, assuming we could capture it. Obviously, capturing all that sunlight is a bit complex in practice, and naturally, if we were to capture all of it, that would be a slight problem for any plants on the planet that need that light for photosynthesis. But even if we got to the point where we were using only half of all that available energy, we would completely get rid of our need for fossil fuels and could have the energy needed to support a much larger population at the same time. Forget 8 billion, we could sustain 40 trillion people here on Earth, at which point the biggest challenge would not be how to give all those people the energy needed to support their lifestyles, but where to put them. Increasing the population density by 5,000 times would change the average of 7 people per square kilometer to 35,000 people per square kilometer, or 1 person per 3 square centimeters. So making this work might be a bit challenging without some creative housing solutions. Regardless, this does seem to be a promising solution to the energy crisis. The joules are there, so if we can already meet our population's needs by fully using only a small fraction of the sun's total output, the part reaching the Earth, we probably don't need to capture any more of it just yet. However, looking to the future, that will not always be the case. Reaching 40 trillion people is actually not that far off, at least on the scale of human history. Our population is currently growing at a rate of 0.88% per year. At times, this number has been as high as 2%. For simplicity, let's use a round 1% figure and calculate using that. If the population size grows by 1% every year, the cumulative growth of the population would reach 8 billion in a decade, 22 billion in a century and 40 trillion in only 800 to 900 years. So, what might be the solution when that happens? By doing as Dyson's imagined alien races do and increasing the amount of solar energy that we capture, likely by building solar panels or mirrors and sending them into orbit around the sun. As the course pointed out, with more solar collection tools come greater benefits. A Dyson sphere, or a Dyson swarm as this segmented setup is technically known, offers power that is many orders of magnitude higher than what we can get with just a planet's worth of surface area. Capturing it would raise us to a higher level of civilization, one that went from controlling its planet to using its entire solar system, maybe giving us the springboard that could truly kickstart our expansion across the stars. On the Kardashev scale, a way of measuring a civilization's progress by looking at how much energy they could possibly use, this would push us from a Type 1 civilization into a Type 2. In case you are wondering, we are currently only about a Type 0.7, as we haven't quite managed to use all the energy on the planet. While a Type 2 would have access to all the energy in the solar system, to reach a Type 3, we would have to capture an entire galaxy, so that is a long way off. Still, the energy levels a Dyson sphere could produce are already so huge that it seems crazy to our current understanding to even think about them. If we finished a Dyson sphere or a Dyson swarm, we would go from 7 septillion joules to 10 decillion joules, increasing our energy levels by 20 trillion times. That should be enough to keep the lights on for the foreseeable future. Technologically speaking, we are nearly at the point where we could build a solar panel able to capture sunlight from the sun and send it towards Earth. Or even simpler, we could just make space mirrors to reflect the light to where it is needed, say an orbiting space foundry outside of Earth's atmosphere, with the same final result. This might be the simpler idea, as then one would not need to worry about how to move all the generated electricity from the solar panel back to Earth. One could just direct the sunlight directly to wherever it is needed, although some livability on the Dyson sphere itself would be sacrificed. Putting mirrors into stable orbits is not impossible for us, and having them able to move slightly to reorient throughout the year does not sound too unbelievable. So then, it is just a question of how much material this would need. Unsurprisingly, depending on the distance at which one made the shell, a Dyson sphere would need a huge amount of material. For instance, the course identified that building a Dyson sphere that matched Earth's orbit would need about 6% of the entire volume of the planet, even if the panels were less than a millimeter thick. This is hardly ideal, even if we could selectively take out the needed materials. But if we instead built a sphere at a much more compact distance from the Sun, say at the distance of Mercury's orbit, then the material needs become much more possible. Mercury itself has all the raw material that might be needed for such a structure, and as far as we know, there is no one living on Mercury who would mind if we were to drill it full of holes. But then the last issue to think about, other than the moral question of whether it is okay to take apart an entire planet just for our own benefit, is that it is obviously an energy-intensive process. Materials must be mined, processed, and then made into their parts. The solar panels or mirrors would need to be built, and even once that is done, they need to be lifted out of Mercury's gravitational well, and that is a particularly energy-intensive process. If we used all the sun's energy that was hitting the planet Earth and spent it all on doing nothing but lifting mirrors for our Dyson sphere out of Mercury's orbit, we can calculate how long it would take us to lift enough mirrors to finish the entire shell. We know the formula for overcoming the gravitational binding energy of Mercury, which for Mercury gives roughly 2 × 10⁻³ joules. We already know the maximum amount of energy we could get from sunlight here on Earth, 4.7 × 10^24 joules. So then, it is simply a matter of dividing the first by the second, and voila. This process would only take a mere 425,000 years, during which time there would be no energy left to support Earth's population or give light to our plants, because we would be spending it all on building a Dyson sphere. Perhaps this isn't such a workable idea after all. But wait, there's one final factor to add: the fact that once our mirrors came online, they could start providing their own energy to help cover the energy costs. This would then become an exponential process, needing no more input from Earth, maybe with the exception of a little oversight. One mirror would provide energy to create a second, then both would double to create 4. In every case, you would be doubling your number of mirrors, and once exponential growth is involved, depending on the initial energy input into the system, the entire project could be finished much sooner. According to some calculations, Mercury would be completely taken apart in as little as 31 years. In other words, if we started building right now, one might live to see it finished. Ethical questions aside, such numbers truly show the viability of this project.